I'm waiting. Huh? No, what speed sensors did we talk about last class? I guess I need to pause. We can use these as speed sensors, right? The rate of the pulses. In fact, we actually calculated the speed of my motor last time. What else?
Talk about
We talked about DC and AC tachometers. We talked about the Hall effect. No, that's light. We're talking about speed. Photoresistors are light sensors. We did finish up on that, by the way. Then we talked about variable reluctance. And I think that's all we talked about. So we talked about variable reluctance. Talked about the Hall effect, right? Talked about the DC tachometers, DAC generators. Talked about incremental encoders, and then of course quadrature incremental encoders. And of course quadrature incremental encoders can also give us the speed, but it can also give us the position, right, and the direction. So we did that last time. We used either one of these formulas right here would work, right? We actually ran my motor at a certain speed. We looked at the output of the encoder, and then we calculated the speed on that. And of course, you're right on light sensors. What was our light sensors we talked about? Photoresistive, right? Yeah, this is photoresistor. Y'all probably heard of it as a photocell, but the technical name is photoresistor, and that's what we'll use, of course. Then we talked about the photodiode, right? Understand phototransistors and also photovoltaic cells, which are solar cells. Okay, and these were the light sensors that we talked about. And I didn't have a photoresistor, and I said I was going to bring one, and I didn't. In fact, I made myself a note. And a phototransistor. We have phototransistors over there too. And we have photovoltaic cells too. So I didn't bring any of those. I'm sorry. Just wouldn't believe what I've been up against. So next time we'll look at it, since we don't have many people here, it'd be a waste of time going to the lab, wouldn't it?
I told me the operations and programs, like, well, the lab part ain't done. Maybe we have to catch up.
Yeah. Well, the problem is we got a lot of people that's not here. One person, I would probably do that. But, first of all, did y'all talk about the Wheatstone Bridge? Did we talk about the Wheatstone Bridge in this class? I think we did. Yeah. What we got is some people draw. Wait a second. Let me start all over. What we're trying to do is establish a zero reference. So I've got a thermistor, and the thermistor varies its resistance with temperature, right? But what I would like to do is establish what zero temperature is. So it's got a certain resistance at zero, and plus it's hard to process resistance. So usually if I've got a sensor that varies its resistance, somehow I convert it over to either what? When I'm starting with a V. Now somehow we're going to convert it over to either a voltage or a current. And the most widely used is voltage, even though current's out there too. So how do we take a sensor, instead of drawing the sensor, I'm going to draw it as a rheostat. How could we take that thing whose resistance varies with what it measures and output a voltage? Oh, Michael? Well, we know we're going to have a power source right over here. And then we're going to take the output of the sensor and feed it over here somewhere. And we want the voltage to vary with temperature. So what else do I need to add with the circuit? I can't come over here and put my power supply right there, because all it would do, if this was a 12 volt supply, I would get 12 volts out there. And what the guy's going to do is going to change current, right? You understand that? So what could I add to the circuit to cause me to get a voltage right there that varies with the resistance? There you go. Thank you. I'd add another resistor. But what I would do is I would come right here and I would put a fixed resistor right there. And so what happens, let's say this was 1K, and let's start this off at 1K. And I got 12 volts. Well, right now, this guy would output 6 volts. Understand that? Okay. And then, of course, let's say my temperature goes up. So we're using what we call a NTC. So we can buy these things as NTC, or we can buy them as PCTs. And this means this is a negative temperature coefficient. We didn't talk about that last class, so that's good. And of course, this would be what? So an NCT its resistance would go down with what it measures. A PCT, the resistance would do what? Would go up. So the ones that we have, these are NTCs. I'm sorry. I said it right, but then I put it wrong up here. Temperature coefficient. Yeah, so I said it right, but then I put it wrong. So the ones that we have are negative temperature coefficients. So that means temperature goes up. So let's say it drops down to 500 ohms. And then what would be my output voltage now? It's not going to be 6 volts anymore. It's going to be less, right? You understand? So we could calculate this. We could say my voltage out would be equal to 500 ohms over 1500 ohms. And then we can multiply that times 12. And that would give me my output voltage. So this formula right here is called voltage divider formula for a series circuit. And what we can do instead of having to calculate current. So most of the time you can, especially on a 2 resistor circuit, most of the time you can calculate RT in your head. You don't have to use a calculator. And so I know this guy right here is going to draw 5. This guy right here is going to drop 3/5 of the voltage. That's not right. 1/3. This guy right here is going to drop 1/3 of the voltage. This right here is going to drop 2/3. Then I would multiply that times. So what we do is we take the resistor we want to find the voltage drop across. And then we divide that by RT, and that gives you the ratio of that resistor relative to that. And then we multiply it times the power supply, and that gives me the voltage drop across any resistor. This is called the voltage divider formula. It's really cool. Because now you don't have to calculate current. So back in DC, you said, well, I want to find the voltage drop across this resistor. You add all the resistors together, you divide that into your total voltage, you get your current, you go back and multiply that back through to find the voltage drop. So what would this drop? So I can mark off this guy, this guy, this guy, this guy, right? And then that 5, and that would be 1/3. So automatically, without even using a calculator, I know that drops 1/3 of the voltage. And what's 1/3 of 12? 4, right? And then this guy right here would drop the rest of it. This would drop 2/3, which would be 8. So I calculated that without even picking up a calculator. So what I'd get out now is I'd get out 4 volts, right? You understand, because the temperature went up. Now, if I needed my voltage to go up, which makes sense, then what I would do is I would put my sensor right here, and then I would put my fixed resistor right there. So the voltage goes down, or V goes down when temperature goes up. Over here, if I do it like this, then voltage goes up when temperature goes up. All I did was change the reference between my, so as this resistance goes down, the voltage drop across that goes up, right? So depending on what you're looking for, what your control system's looking for. But the problem is, even though this is a thermistor, I have no idea what freezing is. Now, of course, it's easier to do in Celsius because it makes sense. So what I would like to do is I would like to get 0 volts out at 0 degrees. And then I want my I would like my voltage to go up as my temperature goes up. Now things make sense. So instead of me getting 3 volts is equal to 0 degrees Celsius, now we can make 0 volts equal to what? 0 degrees Celsius using what we call a Wheatstone bridge. So we use Wheatstone bridges when we try to, one of the main things we can do is we can set a 0 reference. I learned about it when I was in school, but I really ran into this when I got into scales, working on electronic scales. So Wheatstone bridge, and you'll see a lot of people draw it like this, but it's very hard to draw. And then we put our voltage across here. So let's say this is plus 12. And then down here, this would be common. The easiest way to draw it and see how it operates is just to draw it as a series parallel circuit. And what we're going to do is we're going to measure our voltage right here. So let's say this is a 1K, this is a 1K, this is a 1K, this is a 1K. That means this would drop 6 volts, this would drop 6 volts, but we're doing it so over here I got plus 6, over here plus 6. What would my voltmeter measure? It measures 0. Why? Huh? Well, and what our meter measures is the difference in potential. What's the difference in potential between a plus 6 and a plus 6? None. Okay. We say here that the bridge is balanced. And it has to be the ratio. So I could come over here and we could calculate this all day long, guys. But I could come over here and make this a I can make this a 5K, and I can make this a 10K, and over here I can make this a 50K, and over here I can make this a 500K. And this thing would still be balanced. Oops, got it backwards. 5K, 10K, I need to double it, right? So this would be 100K. So let's do it. Let's see if the voltage drop is the same. So this will be 10K divided by 15K, right, times 12. Of course, the K cancel each other out, right? You understand that? Then this over here would be 50K divided by 150K. K cancel each other out. And I can mark off the 0, right? This is 10, right? And hopefully it comes up to give us the same thing. And then I multiply this times 12. So what voltage would I get right here? I didn't screw up. What do we get for this one? Yeah, I did something wrong. So 5K, this is double, 50K, this is doubled, right? So 10K divided by 15, no, I'm sorry. 10K divided by 15, because we're trying to find the drop across this one. I see what I did wrong, sorry. Because they had to be equal. So I just messed them up on this side. So I'm trying to find the voltage drop across this one. So this will be 100K divided by 150K. So this cancels out, right? This cancels out. This is cancels out. But what do you see over here? Now I'm down in 10 and 15. Over here I was at what? 10 and 15. So as long all you got to do to balance the bridge is just have the ratio of the one on the left the same as the ratio of the right relative to the same resistance. That makes sense. So what would happen? Let's go back to the 1K. So 1K is easier to deal with. So let's make this a 1K, and my rheostat, my temperature sensor is on this side. Oops. So this is my temperature sensor. That's my whatever it is, right? And then I'm gonna come on this side, and this is my adjust right here. Say right now, my temperature sensor, I take my temperature sensor, I dip it into a glass of ice water, which now I have a what? I have a 0 degrees Celsius reference. Then I come over here and I adjust this until that meter measures what? 0. And now I've got a voltage that's I got a resistance that's relative to 0. You'll see this used a lot with sensors that vary their resistance with what they measure. Because what I can do now is I can set a what? I can set a 0 reference. And if this goes minus in respect to that, so if it goes below 0, my voltage would be a minus voltage. If it goes above 0, my voltage would be a plus voltage. So now not only do I have a 0 reference, but now I have a reference when my temperature goes below 0 and my temperature goes above 0. So like I said, you'll see Wheatstone bridges used a lot with sensors that varies their resistance with what they measure. Because what does it give us the ability to do? Set a 0 reference. So I've got a scale out there. This scale's got a weigh bridge on there. That dang weigh bridge weighs 15,000 pounds, right? You understand? But I want to make the weigh bridge equal to what? 0. So we had a 0 adjust on there, and that's what we do. We adjust them out until it measures 0. Then we put weights on it, and then we set what we call the span. So what you do is you start off by zeroing out the scale. We put calibrated weights on there. We carry like 100,000 pounds worth of weights. We'd put it on there. We'd say we would tell the thing to weigh 100,000 pounds. We'd lift it up, because anytime you adjust the top, you move the 0, right? And you just keep zeroing it out after that. You know, once you about 3 times going between full load and minus load, zero, you calibrate the scale. And that's what we used to do. And all we were doing was just adjusting water. We Stonebridge. That's all we was doing, just turn those knobs. Eventually they went totally computer, which was really neat. It made it a lot easier. Because you because it did the span for you. So you just hit the zero button, zero it out, you put 150,000 pounds on there, you say 150,000 pounds, and it was calibrated, so it was a lot easier to do. So Wheatstone bridges, where we're going to run into these, only with sensors that do what? Varies their resistance with what they measure. And what does the Wheatstone bridge give us the ability to do? It gives us to establish a zero, right? Makes them
Sensors that vary
resistance. Because we've got to, number one, we're either going to have to convert it into a voltage or we're going to have to convert it into a current. Most of the time we convert it into a voltage because it's easier to do and it's easier to sense. We do have another one out called a 4 milliamp to 20 milliamp, and it's called a current loop. So the advantage of the current loop is that we're developing a current. So the problem we have with voltages is voltages are susceptible to electromagnetic interference, which we call EMI, right? So voltages are acceptable. So usually when we have a system, when we have a sensor system that deals with voltage, it is a high resistance system because we want a high resistance so it don't consume a lot of power. But the problem is if it's high resistance, then it's open up to electromagnetic interference. 4 to 20 milliamp current loop is a low resistance system. So it's hard for electromagnetic interference to create a current. It's real easy for it to induce a voltage, right? You understand that? In fact, it's inducing a voltage with me right now. And I can measure this on the oscilloscope. Sometimes this is good, right? This induced voltage that we can see. This is me. You see? This is me. So I'm having a voltage induced into me right now, but you can't get any current out of me. As soon as I try to get current out of me, it drops to what? Yeah, it drops to zero, right? Let's see that. So voltage systems are very susceptible to noise, so we have to do things. Anybody ever use this technique? Y'all know what we use this for? This induced voltage. You know what we use? Thank goodness. How do you think the touch screen on your phone works? Works off this right here, right? Works off what we call a capacitance effect. So your phone is set up in millions of little grids like this, rows and columns, and when you touch that thing, it picks up your induced voltage and says, okay, there are fingers at this position. And that's why it don't work if you have gloves on, right? You can't pick up your induced voltage. Works the same way. It works off an induced voltage. So if I hooked up the oscilloscope to this thing, I'd probably see the same induced voltage. It works off an induced voltage. Who's not here? So we would use this with on our light sensor side If we needed to measure the amount of light, then this would be what we would use, right? A lot of sensors have a little circuit similar to this. This is called a comparator circuit. And I should draw this up a little bit. And these, you can buy these LM301s. So notice what I'm going to do. Let me spread it out a little bit too to make it clear how this thing works. So the way this thing works is I come up here and I set a voltage with this guy. Let's say I set a +3 volts. And then what happens, as long as this right here is below 3 volts, the output would be 0 volts. And as soon as this thing comes up here and hits, I mean, just as soon as it clears +3, so let's say 3.1, then this output would go to whatever of the powers up the comparator. So these are sensors where you can actually adjust what we call the threshold voltage. So there's a lot of sensors where you can determine where it trips between a outputting a voltage or not outputting a voltage. And so these sensors will have I'll have a little screw setting. Usually they're recessed, so you have to get a little screwdriver to turn them. They usually don't put knobs out there, and why is that? Because people will turn them, people will turn them. So they usually make them a little hard to do. But that's what you're doing. All you're doing is setting the reference voltage on a comparator, and then if it exceeds it, it does what? It just flips. So we use a lot of these. So I could take the output of this, and this could be my comparator, and input that. So these are several circuits. So Wheatstone bridges give us the ability to establish a zero. It gives us the ability to have a negative or positive depending on if you go below 0, the voltage will go negative. If it goes above 0, then the voltage will go positive. And then we still have the ability to do our transfer function, right? How do we calculate transfer function? Out over what? So degrees in, voltage out. Normally we use the maximum, so I get 10 volts at 360 degrees, and then I could get a number of volts per degree. So load sensors, we'll look at bonded wire strain gauges, and then semiconductor force sensors. So what's a force? What's a pressure? What's the difference between pressure and force? Yeah, force is actually doing work, right? Understand that. You can't have work, you can't have force without a pressure. And what's the basic formula for calculating force? Anybody know? It's how much area the pressure is pushed. It's how much pressure is pushed against a times pressure. Area times pressure. So we can't have force without a pressure, but the force is actually doing work. And of course, to do work, anybody know the formula for work? Yes, force times distance or speed, either one, because the further the distance, the faster the speed. So that means to actually do work, something's got to move. So if I go over there and up against this wall and I push on it with my hand, I have a pressure, but am I doing work? No, because the wall is not doing work, moving. So what we're doing with a bonded wire gauge is we're basically measuring a force. So these guys actually move, even though you can't hardly see them. They're going to compress or do something like that. And we're going to translate that force over to some type of output. So what determines the resistance of a wire? The material it's made from. The gauge, or the size would be more correct. Actually, 4 things. Starts with an L. Length. What's the 4th thing? Starts with a T. Temperature. So, wire metals, their resistance goes up when they heat. So, if I can do something with this, then I can change its resistance, and then of course I can control the temperature. How we control the temperature? So what a load cell is, it's a bunch of wire. And it does like this. Probably it'd be better if I drew this upside down, guys. So it always amazed me. I would be working on a truck scale, like a 180,000 pound truck scale with these load cells, and they'd have a big old chunk of metal in them like this. And then this, the actual weigh bridge would ride on top of this thing. And when that truck pulled up on that thing, guess what that metal actually did? It would actually decrease in size this way, and it would increase in size that way. So it would actually, and you couldn't see it, you could not see it, but this is the way these things work. Is the load cells themselves had big chunks of metal in them, and when these trucks pulled on top of that, it would squash that thing down. Now, what did it do? What would happen if I was measuring the resistance of this thing? What would happen to the resistance of it when the truck came on? Well, the resistance would go down because not only did it get shorter, it got what? It got fatter, right? You understand that? Well, this is not what we measured. Is what we would do is we'd slap something on the side of this that would actually have the ability to measure how much it expanded. And this is what we call a load cell. So a load cell is just a bunch of wire, and it's in a bunch of loops like this. And we excite it with a DC voltage. And when a weight comes up in here and hits on this side right here, on vertical, what does it make it do? Well, it makes it squat down, right? The wire length gets smaller, and it spreads out, which causes its resistance to go down. And these are called strain gauges. There we go, right? These are called strain gauges, and this is basically all they are. They're just a bunch of wire, just hut and loop, very small gauge wire. And when the load comes there and hits this thing, these are bonded, so they're glued to the side of this big chunk of metal. So when this big chunk of metal comes up, it either expands or contracts. What is it? It causes this thing to expand and contract, which causes its resistance to change. It don't change much. In fact, it's rated at millivolts. Now, these guys vary their resistance, but the problem is this third thing right here. They vary with what? I'm sorry, the fourth thing. I can't count. Temperature. So we know the length, and so what we're doing is we change the length and we change the width, which causes the resistance either to go up or go down, right? You understand? So since it changes the resistance, then what we would do is we would come over here and put this in a Wheatstone bridge. I'm not going to draw it as a bridge, guys. I'm going to draw it like a series parallel circuit. So we always use these things in pairs. Or we should use them in pairs. I had to remember how to spell rheostat. So what we got is rheostat. No, I'm sorry, that's not true. Sorry. So these things will be wired, they're on the same chunk of metal, and they're right there together. So this is the metal that's measuring. One strain gauge would be mounted like this. So this would be what they refer to as the active gauge. And the other strain gauge would be mounted like this. And what do you think this strain gauge is? The one that's not measuring weight. What do you think its function in life is? Huh? To compensate for temperature. So let's just say this right here is measuring 1,000 pounds, and it's giving me, and my voltage across here, would be 15 millivolts. And then the temperature goes up. If the temperature goes up, the resistance would go up, which would cause this thing right here to keep going up, right? You understand? But what's happening is this guy over here is in there to measure temperature. They're measured right there together. So if this resistance goes up, this guy's resistance goes up exactly the same amount. So what these guys right here, they're going to basically zero out the temperature. But if the weight comes on this and causes this to go up, and this goes up to, 500 millivolts, then that's going to be the weight. So this guy's in there to compensate for what? Compensate for what? Compensate for what? Temperature. So what it does, it keeps a balance, right? You understand? So if the temperature goes up, the resistance of it, both of them go up exactly the same. If they go up exactly the same, then that means that would try to balance the bridge. But if we actually put a weight on the thing, then of course it would give us the active weight. So normally these things are always run in pairs. One of them's called the active gauge, the other one is in there for temperature composition. They're wired 90 degrees away from each other, right? One of them's wired that actually senses the weight. The other one's wired in there strictly and they're exactly the same thing, so they vary their resistance. Unfortunately, guys, we don't have any strain gauges. But all your digital scales out there, this is the unit that it uses to actually measure. These things are extremely accurate. So odds are, if you buy and sell off those scales that use the strain gauge as the sensor. So it's very, very accurate. If you got a set of bathroom scales that probably don't use this, it usually uses the lever system or uses a resistance. Oh, I put them side to side. This is where they need to be balanced, right? Here's, no, I'm sorry. It's just drawn different. Notice here they're putting the power in the center. So the active gauge, here's the force. So the active gauge, this would be the active gauge, this would be in their compensation. And it's look kind of different because I put my power up here and they're putting their power. And this goes to some type of amplifier, which is for a minus or a plus. If the plus is bigger, the output goes plus. If the minus is bigger, the output goes minus. So it'll give us an output relative to. Okay? So they're right there together, and they're glued on there with super glue. You can't repair them, you can't fix them. If the strain gauge burns out, usually we excited these things, and we have to look them up. I don't know if I've got a data sheet on strain gauge now. Right. Just very few of us deal with strain gauges. What they do is they confine all this circuit, your Wheatstone bridge. So here's your Wheatstone bridge. Here's your strain gauges inside this big old unit. And this is what they refer to as a load. So the load cell is the combination of the Wheatstone bridge. It's actually out there. You don't see it. All you got is 4 wires. 2 of them they call excitation. 2 of them they call output. And I forgot the color code. I worked on these things for a long time. One of the times I was laid off from USC, I worked on this field. Interesting job. I just had to travel a lot. So they manufacture them in different ways depending on where the strain gauges are attached. They have what they call split beam. So this is what they call a split beam load cell. So what happens on this one, we stretch it apart and cause the load cells to change. I mean, we have compression type. I said they show us compression type. These are compression types. And these guys right here, guys, we can get these things. And look at the chunk of metal. And that goes down through the thing, and then the load cells are actually, the strain gauges are actually mounted on those. They're not showing any real big ones. Here's one. And I don't know if we can read that. No, I can't read it. I was trying to read the label. So this one can measure up to 5 kilograms. So this would be a big one. But then they give you excitation voltage. So this is the voltage you apply to it. This guy's going to do what? 5 volts DC. And then I'm looking for the output voltage per pound, but I don't see per kilogram. But oh yeah, rated output 1 millivolt per volt. So 1 millivolt per volt, and it's got so 5 volts means the maximum output would be equal to what? 5 millivolts, right? If you excite it with 5 volts, so that means if this was a 10-pound load cell, it would output 5 millivolts when it measured 5 volts. 5 pounds. So it didn't change very much, and we're not talking about a big change, right? But it's enough to measure, and it's very, very, very lean. Well, I worked on some counting scales, and so you'd get 100 straws and put it on top of that thing, and you'd say that's equal to 100 straws, and you'd throw one more straw in there, and it'd go 101. So it could count the weight of a straw. So there's a lot of places that that's the way they inventoried. They didn't sit there and count them. They just do what? They'd get a big old drum that zero the scale out, and they'd start throwing parts in there, and they'd put 500 parts in there, and it'd say 500. It was the neatest thing I ever seen. So one of the big things that we did was just hauling scales around when all these companies these warehouses started doing inventory. Instead of counting, all they did was what? Weigh them. Yeah. Huh? Well, you could weigh it. You could technically. I wouldn't. I think I would do that as an average because I would think the weight of money would vary depending on how old it was. If it was new, I guarantee they could weigh it. But after you handle it for a little while, what happens when we handle stuff? Yeah, we get goop all over it, right? We're a very, very dirty species. We get oil all over the things. The police like it, so that's the way they get fingerprints, right? So these are basically what strain gauges look like. They're little old tiny things. They're usually mounted on a pole, and then you take those. They take them. So what we do is we buy load cells, and we had load cells that varied from. We had the biggest one we had was 50,000 pounds. No, we had 80,000 pound load cells. Then you take 4 of them and put it in the weigh bridge. You put it in each corner, and then of course the weight was varied out over it. So 4 80,000 pound load scales would give us the ability to weigh what 400 pounds. So we had truck scales. We worked on a lot of the truck scales that the Alabama State Highway Department uses to measure the trucks when they come in there, to make sure they're not running heavy. Buy and sell off of. So, yeah, go ahead and take a break and let me. So this is what we was looking at. So this guy, this strain gauge right here puts out 2 millivolts per volt. So that means, puts out 2 millivolts per volt. We excite it with 10 volts. So that means this guy right here would only put out what? Oh, I am recording. Y'all just not seeing what I'm seeing. Because I was looking at the test. So this guy right here, we excite it. We call the excitation voltage. We excite it on 10 volts, and it puts out what? 2 millivolts per volt. So its maximum output would only be what? 20 millivolts. So if I put this on a 1,000-pound truck scale, that means at 1,000 pounds, it would put out 20 millivolts. So it's a very small voltage we get out of these things. Now that's just these strain gauges right here. This load cell right here, though, it puts out 2 millivolts per volt. And now I don't know if that's this one or not. But look at the size of the thing that this thing measures. So when this truck pulled up on there, it would actually cause that thing to squat down and get fatter, and then the load cells, the strain gauges measure that stuff. It always amazed me. Force sensing resistor, polymer thick film. I don't know if I've got one of these over here or not. And I had the list, guys, but I got so done busy with what's going on. Yeah. And this looks kind of like a strain gauge. This is a force sensing resistor, an FSR. It's a polymer thick film device which exhibits a decrease in resistance when an increase of force is applied to the active surface. Optimized for use in human touch controls. Similar to strain gauge, is not suitable for precision measurement. So these work like a strain gauge, but they're not extremely accurate. They're used a lot in push buttons where you just go up there and do what? Yeah, you just hit the button, and it's not a real button. And so I think my TD has a bunch of these on there now. They're not real buttons, they're just pads. You go up and just do what? You put your fingers on there. So human touch devices. So there it is right there, guys. So that's what we're passing around. So you can get your own meter and hook it up to these two particular wires, and you can just touch the front of it and then watch the resistance go down if somebody's got their meter and play around with it. All right. Fairly linear up until they get up to some way. Fairly linear means they vary out to a straight line. It's not a perfect straight line. This is force, but it's not. It's in grams. Y'all know what people use for the weight of a gram? It's equal to about what? It's equal to about what a paperclip weighs. That's a gram, yeah. Very, very light. So this guy right here, we sense very, very little force, right? You understand? So it varies its resistance. So odds are we would hook this up into some type of circuit that's got a threshold on it, like we showed you a while ago. If I actually wanted to get a weight out of it, then I would actually use a Wheatstone bridge, right? We okay? Questions? This is used a lot, especially in produce departments, where instead of they use what we call a calibrated spring. A spring compresses. We can either compress a spring or we can. It's not uncompressed. What do they call it? Extend, I guess. Expand it. And if the metal is made and it's all the same metal and it's all exactly the same circumference or same diameter, then it will expand and contract at a precise force. And so what we do is we come up here, we put our force on the spring. The spring, this one is running compression. The spring would go in until the force pushes back matches the force coming this way, right? Understand that's where it stops. Now the problem is we're going to find out with a lot of our sensors, to get a sensor, we combine it with another sensing device. So what are they combining this with? They're combining it with a potentiometer. But we would call this it's a calibrated spring force sensor. So what they've done is they've taken a mechanical, nothing electrical. This thing does not vary its resistance. This does not vary a voltage. All this thing does is when we push in, it provides an opposite force. And if you ever did a spring, the further you push it in, the harder it is to push, right? You understand? So as soon as the force pushing back on the spring matches the force pushing over here, this sucker's going to stop. But what they got is they're coming over here making this thing move a linear potentiometer. And what does potentiometers do for us? So what do we use potentiometers for? Variable voltage, yeah, so it's a variable voltage divider. So this guy right here would give us a voltage that would be proportional to force. Are we okay? Make sense? Everybody okay? This I made. Anybody got the meter? Did you put it across that other portion? The one I passed around. This one.
Yeah.
Okay, you play around with it. But I'll need it for this. Let me pause this. So this is what we call carbon impregnated foam. And then we put it between two pieces of metal, right? You understand? Well, this is the way mine is. And then what we do is when we compress it, the resistance goes down. And when, of course, if we expand it, the resistance goes up. But mine is set up to work in compression. This is what I made. So we have two metal plates, and in between we have this carbon impregnated foam. And I've got two metal tabs here, so you can hook your meter up to this guy and hook it up just to this metal right here. And then all you have to do is just compress it. And you'll see when you compress it, the resistance is going to do what? It's going to go down, and when you uncompress it, the resistance is going to go up. Since Kareem got his meter out. This was the popular way, you know, when I was a kid, when you walked into a door, the door didn't open itself up for you. Then they came up with these guys and they'd put these mats out in front of the door, and some old stores still have it. And what they'll do is they'll put, and you have to step on it. Once you step on it, you open the door. We still use them in robotics. We call them pressure mats, where we lay these mats out all around the robot. And when somebody comes up there and steps on it, they generate a force, and then the robot would stop. So these are still used a lot in work cells where the robot cannot be enclosed. So there's sometimes we like to enclose the robot, the big robot, inside a big fenced area, right? Understand? But sometimes you can't do that. Sometimes the robot can't be in that. I think we was looking at one for Amazon, and they have a big FANUC robot, and they could not enclose that thing because way things come into the cell and way things leave the cell. So we use these a lot. So these things are very, very popular. In robotics, they call them pressure mats, and that's exactly what they are. Now, they're not extremely accurate as far as measuring weights. I would not buy and sell off these things, right? You understand? But I could definitely use them for a pressure mat or just to see if something was there or not there, right? You understand? So I made that one right there. So guys, that's our force sensors. Is that all of them? No. Is that the ones we go over? Yes, right? So basically what we've done is we've looked at position, we've looked at speed, we've looked at weight and proximity. And we looked at the bonded wire gauge. We look at the strain gauge, right? Everybody okay there? This is usually combined on a unit that we call a load cell. And what it's got is it's got the Wheatstone bridge built into it, right? It's only got 4 wires. 2 of them is where you put the excitation voltage, and 2 wires where you get the output of your Wheatstone bridge. So y'all need to know what determines the resistance of a conductor. What is it? Then we looked at the FSR. So this guy varies its resistance, very similar to a strain gauge, right? But these are usually for low forces. They're not extremely accurate like a load scale. Okay? And then we looked at a calibrated spring. We still run into these. These are extremely accurate. In fact, what they'll use is the spring will act on a lot of your produce scales. The spring is actually what's turning the die. That's what actually turns it out. So they're not electronic. And a lot of stores still have the spring actuated produce scale where you can just throw your produce in there. But when you go up to the cash register and they weigh it on their cash register up there, I guarantee that uses a strain gauge. So strain gauges are probably the most accurate method of measuring the force that we can come up with. In fact, guys, a lot of buildings now put strain gauges on their main columns that go up. And that way they can measure the force on the building, they can measure the sway on the building. A lot of times when they build it now, they'll put strain gauges all over it. And then we talked about just a carbon foam one. Like I said, is this all of them? No.
Hey, Rick, can you go back up to where, so that when we do that, it's not like those there.
That is something
That's how you should know.
this will never be on a review sheet.
Oh, see, I didn't, you said it was doing tests, I didn't get to read it.
Yeah, this will never be on a review sheet, but it'll show up on any test that I do. Just like resistor color code. Resistor color code will show up on any test that I do. I do that a lot. All that's taken my class probably know that resistor color code pops up every once in a while. So this is something you should know. Like what's required to induce a voltage, you should know it. What determines the amount of voltage that we induce, you should know that. That's something that's been covered several times. It's just like in DC, and I need to go back and talk to our DC instructors. They need to be teaching Wheatstone Bridges in DC when they teach series parallel, because that's all it is a series parallel. But this is an application for a series parallel circuit, right? And it's not a complicated series parallel circuit. I mean, it's very simple to do. You might say that's easy for you to say, right? And like I worked on these for years. We was working at U.S. Steel. You know, the way U.S. Steel worked, it was union. If you brought any outside contractors in at the time, then they had to have that worked on electronic circuits. They had to have an electronic repairman there. So they were having problems with the scales, the line scales, and they called in a company called Aero Equipment, and they were going to work on the scales. And who got the opportunity to go over there? Me. So when I got laid off when they built and I got laid off when they built the pipe mill, when they shut it down, the pipe mill, guess who hired me? Aero Equipment hired me. And that's what they did. They maintained and installed all type of weight measuring equipment, all type of scale equipment. So they went all the way from computer control scales down to lever scales, which don't use them, but they were predominantly used these ways. So I learned a lot about load cells. So it was a good opportunity. Only thing I didn't like about the job is we covered scales in 3 states. So we know 4. Georgia, all our neighbor states, Tennessee, and I had to travel all the time, so I didn't like that. I did get to drive a big old scale truck with a 10-speed transmission in it. That was fun. All right, guys, let's go ahead and take a break. We'll come back and go lab. Take a break. Come back and go lab.